Let us begin by defining one of the most important classes of functions in all of analysis, in fact in all of mathematics. These are the functions that are extensively used both within mathematics and outside mathematics in applications to physics, etc. This is the definition of a smooth function. Definition: a function f from AB to R is said to be C infinity of AB, or just smooth on AB if all derivatives of all orders of f exists and are continuous in AB. That means not only do the derivatives of f exist, first derivative, second derivative, third derivative, and so on, they are continuous as well. Note that this continuity part is sort of redundant, simply because if the derivative f3 exists at all points, then f2, the second derivative, is automatically continuous, so on and so forth. We could have just said that derivatives of all orders exist at all points. That would be enough, but I want to emphasize continuity also, so I'm adding that. Okay, now examples, there are plenty. Since I said this is the most important, examples, polynomials are the good class of examples. Then what else? Nothing. All the other functions that we have so far studied, I have taken it for granted that you know. The polynomial functions are the most general class of functions we have studied so far. There are other examples. There are sin x, cos x, e power x, etc., the so-called elementary functions. But so far I have just taken it for granted that these functions are defined and have the properties that you are familiar with. We have so far not yet defined these functions precisely, which is sort of going against the goal of this course to define everything precisely. So how are we going to define these commonly used smooth functions? Well, one idea motivated from the previous theorem about Taylor, which I have sketched, is why don't we just write down the Taylor series of e power x or sin x or cos x and try to see what happens. Well, we already know that the characteristic property of e power x is that d by dx of e power x is equal to e power x, and e power 0 is 1. Okay, e power 0 is 1. Immediately, if you start writing down the first few terms in the Taylor series of this function e power x at the point 0, you will get that e power 0, which is 1. So e power x will be 1 plus, then the first derivative of e power x is just e power x, and at 0 it's 1. Then you will just get 1 plus x. Okay, then you will get x squared by 2 factorial, because again second derivative of e power x is just e power x, and at 0 it's just 1, plus x cube by 3 factorial plus dot dot dot. Okay, what I have done is I have taken the Taylor's theorem that we have before, that if you have a function that's k plus 1 smooth, then you can write the function value at x as the values of f of 0, f prime of 0, f double prime of 0, that is essentially this Taylor polynomial plus a remainder term. What I'm doing is I'm throwing away the remainder term and making this an infinite series. Now question mark is, which I should put a giant question mark here, is this true? Is it really true that e power x is equal to 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus so on? Okay, that's the question. If in fact it is true, then we can just reverse engineer the whole damn thing and just start by saying that e power x is just this by definition. Okay, we can just start our definition of e power x is this, and then show that it has all the properties that characterize e power x, namely these two. Okay, now that's the idea. Now before that, why would you even suspect that this right hand side, this infinite series is not equal to e power x? Why would you even have a doubt in the first place? And that doubt comes because of the existence of many peculiar smooth functions, and that is one of the most famous functions in more advanced mathematics, which is extensively used in the theory of manifolds. This is called the bump function. I mean, this is not essentially the bump function. The bump function can be constructed using this function, but I am going to call it the bump function. Actually, better terminology would be infinitely flat function. Infinitely flat function. You will construct the bump function in the exercises using this infinitely flat function. How is this function defined? Well, let me just immediately begin with the lemma, which will have the definition in it. Lemma. The function f from R to R defined by f of t is equal to e power minus 1 by t if t is greater than 0, and 0 if t is less than or equal to 0 is smooth. Okay, this function, which is defined in two pieces as e power minus 1 by t if t is greater than 0 and 0 if t is less than or equal to 0, is actually a smooth function. A picture, I urge you to draw a picture of this function, will look something like this. In the negative axis, it's actually fully 0. It's just fully 0, but it is sort of infinitely flat at the origin. It's sort of infinitely flat at the origin. It attaches to this straight line that is nothing but the negative x-axis in a smooth way. So this function sort of becomes infinitely flat as you approach the origin from the right. Okay, now what is this function trying to tell us? Well, if you were to write down the Taylor series of this function, the infinite Taylor series, you are in for a shock, because f prime of 0, f double prime of 0, and so on and so forth are all 0. All the coefficients in this Taylor expansion will be 0. So if you were to write down the Taylor series of this function, you would get a giant 0, which is obviously not equal to e power minus 1 by t, which is what the function is when t is greater than 0. So the Taylor series of a smooth function might not have anything to do with the function. We are getting a giant 0 here, whereas the function is e power minus 1 by t when t is greater than 0. So it is not always true that the Taylor series, the infinite Taylor series that you just write down formally will agree with the function. That might not always happen. Let's first see a proof that this function is in fact smooth. Okay, so all we have to do is that we only need to check that all derivatives, or better yet, derivatives of all orders exist at 0. Okay, the reason is that 1 by x is a continuous function. 1 by x is in fact smooth function, is a smooth function outside of 0, and so is exponential. Let me just write 1 by t, or rather in our case minus 1 by t, and so is exponential. Therefore exponential power 1, exponential of minus 1 by t, which is going to be a composition of smooth functions, will be smooth, which you can prove by induction. It's an easy argument to show that e power minus 1 by t will be smooth everywhere except the origin. The origin is the only problematic point where two different functions are being joined. Of course, what I said about e power minus 1 by t being smooth applies only to t greater than 0. For t less than 0, you don't have to do any work. It's just the identically constant function 0. So the only problematic point is the origin. First of all, e power minus 1 by t converges to 0 as t goes to 0. This is just a well-known property of the exponential. Well-known property of exponential function. Okay, this means the given function f is continuous at 0. At least we are off to a good start. Continuity follows easily. Okay, now we have to show that the function f is actually differentiable at the origin. We have to show that it's differentiable at the origin. If at all the function is going to be differentiable at the origin, the derivative has to be 0. That's very clear because the function is identically 0 whenever t is less than 0. Okay, so when t is greater than 0, d by dt of e power minus 1 by t is just minus 1 by t e power, sorry, this is not correct. It's just e power minus 1 by t into d by dt of minus 1 by t, which is 1 by t squared. Okay, we now have the following claim for t greater than 0, the kth derivative of f is of the form pk of t times e power minus 1 by t by t power 2k. Okay, where pk of t is some polynomial. We have already dealt with the base case. That's what d by dt of e power minus 1 by t equal to e power minus 1 by t into 1 by t squared is essentially saying. What I am saying now is that this is true for all derivatives. So assume by inductive hypothesis that fn of t is actually of the form pn of t times e power minus 1 by t by t power 2n. Okay, now we'll have to show the same thing for the n plus 1th derivative. So f n plus 1 the derivative at t is going to be nothing but pn prime of t times e power minus 1 by t power 2n. I'm applying the product rule first, plus pn of t into the derivative e power minus 1 by t power 2n prime. Okay, now how do you differentiate this? This is just going to be, I'll just concentrate on this term, e power minus 1 by t by t power 2n. The derivative of this is going to be nothing but e power minus 1 by t divided by 2 power 2n plus 2. I'm essentially differentiating the numerator, which is e power minus 1 by t, which is going to give minus of 1 by t squared and another minus sign. Both will get cancelled, so I'll get 1 by t squared. This 1 by t squared I'm attaching to the denominator, plus the derivative of 1 by t power 2n. Okay, that is going to be minus it's going to be minus 2n t pk of t, that pk of t is not it here, minus 2n t times e power minus 1 by t divided by minus 1 by t divided by 2t power 2 into n plus 1. Okay, so please check this. Please check. Okay, so I have just differentiated 1 by t power 2n and we get this. Okay, now what does all this give us? It's going to give that f n plus 1, the derivative at t, is nothing but t squared p n prime of t plus pn of t minus 2n t pn of t, the whole multiplied by e power minus 1 by t by t power 2n plus 1. Okay, so this is just a routine computation. Please check or check the notes for all the details worked out. Okay, so we have proved this. We have proved the claim. We have proved the claim by induction. Proved the claim by induction. So now we exactly know how f n plus 1 of t at t greater than 0 is going to look like. Okay, now what is our aim is another claim which is going to be proved again by induction. Claim is that fk of 0 exists and is equal to 0, which is what we want to show, which is equal to 0. Okay, obviously if fk of 0 exists, it's got to be equal to 0 because the left hand derivative, when you take just derivative from the left, it's going to be 0 because that function is just identically 0 when t is less than 0. Okay, so what we have to do is to show that when you take the derivative from the right, you still get 0 for this to work. Okay, so assume again by induction that fk of 0 is equal to 0. Fn of 0 is equal to 0. Assume that you have shown this. Okay, so let me just make a remark if this is confusing. This is for k greater than or equal to 0. Okay, we have already shown that f of 0 equal to 0, so the base case is essentially done. Recall that when you put f0, you just mean f. When you put f0 is just another thing for f. Okay, so you're taking fn of 0 and we want to show that it's going to be, we are assuming that it's going to be 0 and we want to compute the n plus 1th derivative of f at the origin. Again, what you do is, this is nothing but fn of t minus fn of 0 divided by t limit t going to 0 plus. This is nothing but the definition of the derivative from the right at the origin. We already know that fn of 0 equal to 0 by induction hypothesis. So this is just limit t going to 0 plus of fn of t divided by t. Now you might understand why we tried to claim that fn of t is of a particular form. We know that fn of t, this is going to be of a particular form. What is fn of t? This is just pn of t e power minus 1 by t divided by t power 2k divided by t. That's what the expression inside is going to be. Okay, so this is just pk of t times e power minus 1, not k, this is n. This is n. pk of t e power minus 1 by t by t power 2n plus 1. Okay. Okay. Now set 1 by t to be equal to some x. Set 1 by t to be equal to x. So this entire expression will just become pk of 1 by x t power 2k, sorry, x power 2k plus 1 divided by e power x, and now we have to compute limit x going to plus infinity of this. We have to compute limit x going to plus infinity of this term. Okay, but this was already given as an exercise. You have already solved, you have already shown that as x goes to infinity, this quantity, this converges to 0. Okay, this is one of the exercises which was first given just for sequences in the chapter on sequences, is again for functions in the chapter on continuity and limits. Okay, so this first term goes to 0. Okay, and this polynomial, as x approaches infinity, 1 by x approaches 0, so this is going to go to some fixed constant, so this whole thing converges to 0. The net upshot of all this is that the right hand derivative of f exists of all orders. Right hand derivative of all orders of f exists and is 0. So the net upshot is this is a smooth function. The function f is smooth. Yet all derivatives of f at the origin are just 0, which means when you write down the Taylor series, you will get a giant 0. So it is not true that if you have a smooth function and you write down its Taylor series, infinite Taylor series, you get anything useful. It is not always the case that you will get anything useful. So now we are going to begin the topic of power series. We are going to study the general situation under which it happens that the Taylor series does in fact converge to the given function. Then we are going to reverse engineer and define exponential and trigonometric functions directly using these power series and prove that they have the basic properties that they indeed have. We have taken it for granted. Whatever properties we have taken it for granted, we are going to prove that they indeed have those properties. This is a course on real analysis, and you have just watched the module on smooth functions and Taylor series.